Okay, we're back to section 1.1.2. This is a read-along video with Dr. Powell in the book Discrete Perspectives in Mathematics. Okay, so we've introduced what the idea of a function is, what domain and codomain are, what it means for a function to be well defined. So we're going to be looking at some notation and terminology as we go along. First of all, we have this membership symbol here. This means is an element of, we write x is an element of A to mean that x, well, I just said what it was, x is an element of A, all right? And if you cross it out, it just means that it's not an element of A. So what is A? A is a set, x is just an element, something that could be in that set. So, all right. That's one of the notations we can use, and there's different examples that you can look through here. We have a notation. This is called set builder notation for defining what goes into a set. Here's an example. What is this? This is a representation of all integers that are greater strictly than -4. So the set -3, -2, -1, and so forth. Notice that the first part tells you specifically what, and then the second part tells you a condition, and that's kind of right here. So what, we're looking at integers, the integers that are greater than -4. So we can define sets in such a way. Here's another example of defining a set. So the what, ordered pairs where both are integers. But the condition is you don't want the second guy to be 0. Okay. So, you could also write this, you could also write it this way right here. You could say ordered pairs x, y, and then maybe the condition, you can actually specify a, we're letting x be in z and y be in z. This is another way of writing it. There's both ways are fine. But specifically we have the what and we have the condition. Notice that we're using variables in here to describe things, and they're kind of free in some sense to wander according to these conditions as much as possible and develop and build up the whole set. Hence set builder notation. It's kind of building up as it goes through all those different conditions. Okay. So we go through and we talk about certain types of terms. Now notice here these keywords. If you're reading along in the digital version, if you click on one of these image, it takes you to a definition and a glossary. You can click back and it takes you back to the page. If you're in now, if you're just reading in a paperback version, you can go to the end of the section where the glossary is, and then it tells you where to go back to get back to where you were reading right there. Okay, so now remember how we have this notation right here, this assignment arrow for defining what a function does. As a rule, it takes something and it outputs something else. Something in the domain and assigns something in the codomain. The specific thing that it assigns is called the image via that function. So a function is kind of like a lens or something that you're looking through. And what's beneath the lens is kind of like the domain. And what you're actually seeing is what's come through. So it's the image. So if there was something in the domain here, you're looking at a lens, and what has the lens done? It's changed it, relabeled it, and to something else. And so it's the image of what it was, but it's the image you actually see. So we call it an image. So for instance, if we have the function f of x is equal to the absolute value of x, what happens here? You put in -1, what comes out? 1. So 1 would be the image of -1 via this absolute value function. Okay. So we have that basic idea. I also kind of have this term here. You can look at that subset. It's just a part of a set. You can look at that. Here's another one, map. That's just another name of a function. Okay, so here is an example of, this is actually the absolute value function that we were just looking at, where we specified what the domain and codomain should be. The domain we specified to be this right here, and the codomain we specified to be this right here. And as we follow through with this, notice what we've done with it. So the absolute value function. So we took, well, so what we're doing is we're taking a subset of the domain, and then we're applying the function to that subset. What does that even mean? Usually functions behave on elements, right? In the domain, you put an element in and you get an element out. Well, we can also do this with subsets. You take a subset of the domain, like -1 and 1. What's the output of that particular subset? Well, or what are the potential outputs? Basically, what are the set of images of all the different elements in that subset? So here, -1 and 1 both have the image of 1, and so we output the set 1, all the set of elements in the codomain that have that. But notice that if we went here, -2, 0, 3, for every one of these things that we put in, we get a separate image, 0, 2, and 3. And so that particular subset would be the image of, so this is kind of like the image set of this particular subset in the domain. So the word image can apply to subsets as well. You have a subset in the domain, and what are all the sets of outputs that can come from a particular set, and these are that. It's kind of the same way as thinking of if the function were restricted to this set, so this became its new domain, what would the range be? And that's the image of that. It's what comes out of it. Range just means what actually is coming out of the function, not the codomain, but what actually comes out. And so really, that's what image means. It's another way of basically saying range if we've restricted our domain to something. Now, if we restricted our domain to a single element, then yeah, then that would be the range just coming out of it. But kind of to give it a sense. So you can have the image of a subset of the domain. Well, this is kind of interesting because really what we've done is we've created a new function based off of our old function where the domain is actually subsets of, like A, let's let A just be a subset of the domain. And here, see this notation, f of set. We can put a set in and we can get a set out. You've just made a function that goes from subsets of domain to subsets of codomain. This is a function that's induced from the other one. Function f has induced a new function, and where we've come from subsets of D to subsets of C, where D is the domain and C is the codomain. We need some notation here. Power sets, a term here. Power set. Now notice here, notice how in the digital version I get this type of symbol. You can also click on this that takes you to the glossary as well. And then you can go back and forth. So what is a power set? Power set of a set is basically the collection of all subsets of that set. So for instance, let's suppose that we have the set 1, 2, 3. What is the power set of this set? Well, everything here, all the potential subsets. Notice that I included this one, empty set. That's always included in the power set. So power set includes the set of taking nothing, the set of taking just one thing, two things, all different possibilities of that, and 3 and so forth as we go along. So that would be the power set of a set here. And we have a notation here. We use this symbol, kind of a 0 with a line through it, or a circle with a line through it, and that to mean the empty set. Now here we have a little description of, as you look through here, of deciding how big a power set is. Well, if you take your original set, like let's suppose it's A, and if you thought of, so if you're thinking about a subset, let's think about zeros and ones. So if we think about taking the first guy, the first element, then we're making a decision. Do we take it or do we not? If we take it, let's let 1 be we take it, 0 mean we don't. So 1 would mean we take it. Go to the next guy. Let's think, do we take it or not? Let's suppose we don't. If we don't, we'll think of a 0 right there. And if we take the 3, let's think of a 1. So what we do is we have a code, 1, 0, 1, which means take the first guy, don't take the second guy, take the third guy. Now, all possible codes of doing that actually represent all subsets. So basically, we're thinking about subsets as being strings of 0s and 1s, binary strings. We've encoded all the potential subsets. Notice as we do that, if we had a subset of just 0, or we had a code of just zeros, that would be the empty set. We're not taking anything. So, and thinking of how many different possibilities of having those codes, basically we're just doing 2 times 2 times 2 for a string of 3 different things. So 2 cubed. So really we just take the number of things in this set, like 3, and we just say 2 to the third, and that's how many different subsets there are. In fact, we can kind of look at that. Notice there's 8, 2 cubed, different subsets. So we can find the size of power sets. Okay, here's a symbol. This is the subset symbol, where we're saying that something is a subset of something else. We also have another symbol called the union symbol. Basically, what that means is you're looking for a superset of both of 2 sets. So suppose you have A and B. You find a superset, which means a set that contains both of them, but the smallest one that contains both of them. So for instance, let's suppose we have the set 1, 2, and 2, 3, 4. Notice that if we just take 1, 2, 3, 4, that works because it contains 1, 2. It contains 2, 3, 4, and it's the smallest one that does it. 1, 2 is in C, and 2, 3, 4. This set is a subset of C, and it's the smallest one that does. So that's what a union is. Basically, you just take all the elements in all sets, but then you kind of merge what's the same, or you don't double count. Intersection symbol is a similar idea. You take something that's a subset of both A and B. That's the biggest subset of both. That's has the shared idea of being a subset of both A and B, and it's the biggest one that actually fits the bill and does that. For instance, in this particular case, 2 is the biggest subset that's both a subset of this guy and this guy. This kind of the singleton set. When a set only has one element, call it a singleton set. Okay, so we have that kind of notation going on. We're going to use that notation now to help us build up another induced function from a function called the preimage function. Preimage function, which is kind of reversing what the image function does. We're kind of going to the other side of the lens a little bit. And we're just thinking about subsets again. So basically what we do is we take a subset of the codomain. So notice this power set of codomain. So we take a subset of the codomain and we're seeing, well, where could it have come from, right? Where could it have come from in the domain? So where, like, what subset of the domain could it have originally come from? So now with this preimage function, let's look at some examples and we'll keep talking about it. All right, so here we go. Let's suppose we have this function here. 1, 2, 3, 4, 5, 6 is the domain, and the codomain could be bigger or smaller, but the range in particular, we're looking at outputs of 4, 5, and 6 here. Okay, so but let's let our codomain, in fact, let's let our codomain be a little bit bigger. Let's add the number 7, and even though we don't see it, maybe the data type is we could have the number 7, but this particular function doesn't actually get that value out. Okay, so this preimage function actually is a function from the power set of C. So meaning that subsets that contain 7 are actually still in the domain of this induced function. What would be the preimage? Like, where does something like that come from? Let's think of this about this for a minute. Let's think about the number 4 right here in the codomain. What's its preimage? Well, it's going to be a set because there's 2 things that go to 4. Notice 1 and 3. That's like the preimage of the singleton set 4. That's just an example. Now, what if we had 4, 5? Now, what's the preimage of 4, 5? So let's see, 4, 4, 5. What has an image of 4 and 5? Well, going backwards, so it's 1, 3, and 6. So 1, 3, 6 would be the preimage of the set 4, 5. So we've taken a set in the codomain, a subset of the codomain, and we've gotten out a subset of the domain that way. Okay, dokie. Well, let's look at 7. What's the preimage of 7? Singleton set 7. Well, I don't even see it right here. So do you know what that means? It's the empty set. We're letting the empty set. It's the key here is that when we make a power set, we're including the empty set. So we actually can have a function here even when we include 7. So it enables us to do that. So the preimage of the singleton set 7 would be nothing, the empty set. You could go the preimage of the subset 6, 7, and basically it's just the preimage of 6, which is 2, 4, 5, because 7 doesn't contribute anything. So you really can have this. And as you go along and look at these particular examples that I've written out, hopefully that helps you work through the details of that discussion. Here's actually a function table for the preimage function here that we've been discussing. So we input something in the codomain and we output something in the domain, a subset of the domain here of the original function. Notice that when we take the preimage, that's what this function is right here. It's a preimage function. We take the preimage of the full codomain, we actually get the full domain. In fact, even if we have a little bit smaller than the full codomain, because 7 really didn't have a preimage, we still get the full domain as well. Okay. Now we have this term right here, a fiber. What is a fiber? A fiber is simply a preimage of a singleton set. So in particular, so 4, that's in the codomain of that set we were working up there, and its preimage is 1, 3. So we call 1, 3 the fiber of the fiber over 4 via the function f. You could also think of it as the collections that actually merge together that actually have the exact same image in the end. So for instance, let's go back to the original function just to look at, in fact, it's right here. Okay. So think about the fiber over 4, or the fiber of 4 via this function is what? It's 1, 3. What's a fiber of 6? Everything that goes to 6 is 2, 4, 5. So that's the fiber of everything that goes to 6. What's the fiber of everything that goes to 5? It's just 6 itself. Okay. In fact, we can label the fibers just reusing this preimage notation. So we take the preimage of 4, which is in the codomain, and we and so if this is like the input of the preimage function, this is the output of the preimage function. Notice I didn't really label it or write out it, but this is just so we can kind of see what's happening. If you notice, you take something in the codomain like 4 and 7. What we're looking at is we're looking at the union of the fibers of each one of these guys, 4 and 7. So the preimage of 4, the preimage of 7, we union them together. Notice that 7 doesn't contribute. The preimage of 7 doesn't contribute anything because it's the empty set. In fact, if you look back here at this function table that I had up here to compare notes, notice that we have 1, 3 as the preimage of 4 and 4, 7 both times in both cases. Okay, and we can similarly think of the same idea for the image function in terms of fibers. But here we take any non-empty subset of the fiber over 4, and it's always going to go to 4. Why? What does it mean to be a fiber over 4? It means it's something in the domain that actually goes to 4. So if you plug it into the function, of course it's going to go to 4. Anything in there would. Any non-empty subset of this would actually have that, because all those elements would go to 4. You don't have to full fiber. You can have part of the fiber and still the image will still go to 4. Similarly here, you can kind of look at the description here and study that out and think about it a little bit. Okay. And look at those examples. So we have something, so we have a fiber function if you want to think about actually going from, instead of the power set of the codomain, just go from the codomain itself. So you're just looking at singles and sets and subsets of the codomain, and you're going back to preimages. We call that a fiber function. All right. So, so we can kind of think of it that way. Now, if every fiber itself happened to be a singleton set, then we could say that an inverse function exists, and it would be 1-to-1, because then we actually have a function from a set to a set, and not just a set to subsets. So we're kind of generalizing what we've done before if we think about 1-to-1 functions and so forth. But we're going to have some notation, some diagrams to kind of help us out a little bit with this. So often we look at functions with tables, but we can also look at functions with such a diagram, which I call chunking or a fiber diagram. Let's suppose that we have a function that goes from a domain set D to a codomain 1, 2, 3, 4, 5. So everything in the codomain 1, 2, 3, 4, and 5 has a potential has a preimage. Notice that 5 has a preimage of nothing. 4 is preimage of age. So basically, don't worry. This diagram actually is a definition of the function. What? So that means you take the element A in the domain, and where's it go? It goes to 1. Because it's a fiber diagram, okay? So 1 is in the codomain, and this is the preimage of 1. So if you want to know where it goes, you find the box where A is, and it goes to there. Okay, so A goes to 1, B goes to 1, C goes to 1. So all these guys like merge together in the relabeling process of this function. D and E merge together to 2. F and G merge together to 3. H goes to 4, and nothing goes to 5. Okay, so this is called, you can call this a fiber box or chunking type diagram. Okay, so let's look at some terms: injectivity, surjectivity, and bijectivity. So a function can be described as being an injective function, a surjective function, or a bijective function, or neither, or none of these. These are words or adjectives which can be used to describe a function, and it's very nice to see these definitions with a fiber box diagram. So a function is injective if you're looking at, in a fiber box diagram, if you look at all the fibers, which we're putting as boxes here, look at all the fibers, and if there is never more than one in a box, one thing in one of these boxes, then the function is called injective. So it's kind of like the domain kind of injects to the codomain here, injects to it. There's no merging. Okay. So notice even even something like this with the domain of nothing. I mean, you could call this injective as well because there's no more than one thing in there. I suppose if you thought of that as a function. Let's look at another example of a function that's surjective. So surjective means it doesn't matter how many things are in the boxes, as long as all the boxes have something in it. You don't have any empty boxes. So in injective functions, you could have some empty boxes, but for surjective functions, the idea is you have no empty boxes, but it doesn't matter how many things you have in there. Okay, so that's surjective. Bijective means it's injective and surjective. So all the boxes have something in it, but you can't have more than one thing in it. So every box has exactly one thing in it. So it's bijective. Basically, it's a straight relabeling from domain to codomain. Just naturally injects and surjects over. Okay, we will go to, okay, so what we've just looked at, okay, so that takes us to the next subsection here, and we'll end this video right here at this point. Thank you so much for watching.